Hi everyone, we are C4RT and we have a stockbot, a robotic storage and delivery system. Our team members are Ife, James, Daniel, Anan, and me, Suleiman. Our sponsors are Fetch and Kinova. So first let's talk about our project Touchstone. We actually providing a solution for fetching. We're actually providing a solution for fetching, transporting, and managing equipment by using robotics and automation to save employee time and reduce the labor cost. And we potentially have those use cases in the warehouses, factories, laboratories, hotels, restaurants, libraries, and hospitals. So our approach to design, as you can see, this diagram make a summary for our process to the design. So starting from secondary research, we did some competitive analysis, technology, and business research. And then we moved to primary research. We did on that some interviews and some surveys, and we got some insights from this, from the primary research to make the design. And then in the design, we defined the system requirements and features. Then after that, we provided our first prototype with the low fidelity for testing. And we did some user testing. And in the user testing, we did user evaluation. We get some feedbacks. And then we redesigned our project. And we come up with the final product or final prototype for the functional testing and to make sure everything is working fine. Now I'll move things to James.
Our design utilizes two robots. There's a fetch mobile manipulator for transporting items and a Kinova Gen 3 arm that's for kitting items. It's much more accurate, but it cannot move to other locations. For user testing, we used a lot of physical prototypes because our system, being robotic, is very physical in nature. We also made extensive use of the Wizard of Oz method of user testing, where instead of implementing the full automatic behavior, we actually just remote control the robots because it was faster and enabled us to iterate more quickly for our user testing. For functional testing, we essentially just had the robots perform repetitive autonomous tasks and make sure that they worked correctly. Our solution consists of four main parts. We have a storage system which utilizes a Kinova robotic arm. We have a transportation and delivery system which utilizes a fetch mobile robot. We have a backend consisting of a decision engine that routes messages between the other components. And we have an interaction layer which includes our web application and also some human-robot interaction. Here's our demo video. Oh, here it goes. So here's the makerspace where we designed and tested our robots. The student will use the web application that we built to request items from the system. When they hit checkout, it will send the message to the Kinova, which will then pick the items out of the storage location and place them into this tray. Next, the fetch will pick up the tray. You can see it's scanning the environment right now, so make sure it doesn't hit anything while it picks up the tray. Once it affects the tray, it will head off to the makerspace. It's navigating autonomously using visual SLAM and also visual markers we placed on the ground. Now the fetch will place the tray onto the ground and it will let the user pick it up. And once the user has the tray of items, they can then remove the items from the box. So once they're done with items, they can put them back in the boxes and then put the boxes back in the tray and then click return in the web application. And the fetch robot will come and pick up the tray. The again, you can see the fetch scanning in behind it before it picks up the tray. And now we'll head back to the storage location. So we'll put the tray back. And now the Canova arm can take the items from the tray and place them back into the storage location.
For our primary research, first we make some interviews. We interview class instructor, lab manager, GIX staff and students to understand how the process is performed and also to see the challenges of the system. Also, we send some surveys to students to see how they acquire items using the check room. Check room is the application we use here at GIX to ask for items. And also we send a survey for potential users to understand the concerns and the features that we could add to our system. Then for our user testing, we perform two methods. The first one was one-on-one user to understand how users interact with the hardware and the software. We ask the students to check in and check out items, and then we take notes and video to then analyze and see how users interact with the mobile robot. Also, we have the fly-on-the-wall method. This is for the human-robot interaction part. We observed the students like around 20 minutes while the fetch was navigating automatically into the makerspace and see how they feel and how they react having a mobile robot in the workplace. Here are some findings of our testing. We've found that the users have issues with trying to understand the robot intentions, also the interacting with the tray, and also the people are more alert when the robot has sound, because if not, they tend to ignore it. And here's one of our improvements. First, fetch raised the torso to give the items to the users, but then we decided to place into the floor because they were having issues trying to see when the fetch will do the next move.
Alright, now let's move to our hardware architecture. As you can see on the left-hand side, there's our fetch onboard computer and the Kinova onboard computer. Those two computers are talk to the internal components through Ethernet. And for Kinova, we have a specific Kinova server that is essentially another computer that's running our OpenCV algorithms. That is talk to the Kinova onboard computer through Ethernet as well. And our decision engine in the middle is talking to the fetch onboard computer and the Kinova server through Wi-Fi, so as the web app server that's also in the same network. And the web app client is talking to the server through internet. Next slide, please. And here comes our software architecture. As you can see, we have the fetch module, Kinova module. Fetch module is including a navigation stack, a grasping stack. Kinova module is only having a grasping stack there. In the decision engine, as you can see, it has a whole bunch of gRPC remote procedure calls. We use that to implement a message queue to communicate to provide communication between all the modules. It also has a planning stack that will do dynamic message loading to make sure it's optimal performance. And we have the web app module that uses a SQLite database to store customer information and Flask to implement the framework. Okay, next slide, please. And here's our user experience flow. As you can see, we have two pre-built pipelines. The first one is checkout. To provide checkout, the student first place the checkout order on the web app. Then the decision engine will do the loading and message planning. Then it will send the Kinova to do the kitting. After the kitting is done, fetch will do the transportation. And after the transportation is done, user get their item right next to their table. The checking pipeline is essentially a reverse of our checkout. Next slide, please. And our prototype iterations here on the left, we have our iteration 1. That is our web app has the check-in, check-out functionality. The search engine support multiple robot and the dynamic message loading. However, Kinova ARM is currently using open loop control on the ARM, and Fetch is using the standard ROS navigation stack. And move to our iteration 2, Kinova ARM now is incorporate OpenCV algorithm and RQ markers that will provide a closed loop control. And Fetch is using not only the navigation stack, but also Intel tracking camera that will provide better navigation performance. Move to our iteration 3, Fetch is not only the tracking camera, it also integrates with the RQ marker, which will periodically recalibrate it to further enhance the navigation performance in a human environment. Right?
Our product is to free up human employees, so the cost of manual labor could be saved. Here is the warehouse case. We have estimated and calculated as below. In order to have 24/7 operation, which is 168 working hours, normally an employee works for 40 hours a week, so the warehouse should have 4.2 employees. And for the stock bot, it needs only 2 Fetch mobile manipulator for picking, as they could take turns for charging. Also, we need 2 freight research platform for transportation. They also take turns for charging too. And 1 Kinova Gen3 is a type for kitting, which is tagging, so it didn't require to take turn. Next page. So let's calculate the year cost for this demand. With manual labor, each employee will cost $50,000 per year, including salary, tax, insurance. So it requires around $2 million for 10 years in total. And for our product, the warehouse just needs to purchase the robots, 2 Fetch molecular, 2 freight platform, and 1 Kinova Gen3, and paid $10,000 for support freight each year. So in 10 years, it will only cost about $319,000. Next page. So the conclusion is that the human employee costs 5.4 times money as the robotics. Our solution could save a lot for a 10-year period. In longer period, it could even be cheaper. Next page. So in the next stage, we could have some upgrades development. In the hardware level, we have planned server stacks, including optimism storage system and trail design, adding sorting stations and more sensors, and some different interactions. And in the software aspect, designing new UI improves RAM and root planning algorithm and creates new pipeline for those packages. So next page, that's all. We are C4RT team. Thanks a lot for all the help we get from you.
Thanks, team. That was great. Any questions from our audience or online?
Hi, this is Andrew. I just have a quick question. What happens if someone selects something and it isn't there? Because you showed something where it always selected. What happens if it's missing? Yes, if it's not in there.
So if it's already been checked out, we won't display that in the web app front end. If there's a misplacement or some random issue happen, this stuff is not in there. Currently, we don't have it implemented, but in the future, we will have some checking mechanism to check if the stuff is actually inside the box or not.
Any other questions? I have a question for you.
What's the also?
I'm imagining a situation where maybe you've been able to use OpenCV and these machine learning protocols to have the robot do some pretty simple tasks. And say you want to roll this out at a company. Did you think about having a development pipeline where a operator could use and control the robot for more advanced tasks, and then that data was stored somewhere and used to continually upgrade and improve the automated capabilities of the robot? Did you think about software design and application architecture design for that?
Yeah, this is actually one of our key feature of our decision engine. So as you can see, we've mentioned we have a check-in pipeline and check-out pipeline. All those automatic feature is being developed in a pipeline feature, which means in the future we can support low-code deployment, which basically we provide a couple of modules to our customer, and they can just drag and drop and do their own pipeline to achieve whatever task they want.
Cool, thanks.
All right, I have a totally different question. I wonder if you just tell us one nice insight from your journey working together on this project. What was your biggest surprise or your biggest learning from this experience?
Yeah, for us, it was interesting to see when we built the robot and we programmed it, we knew what it was going to do, and that's some feedback. Okay, we knew what it was going to do, but when we actually tested with users, it was not nearly as clear like what they were supposed to do. So that was one of the big challenges we faced. Like, how do we communicate to users what the robot is going to do before it interferes with them?
Also, while having a mobile robot in an open environment, we learn about how hard it is for robots to tell people what it's doing, because robots have no expressions. It's kind of hard to understand if the robot is speaking or making a sound alert. People sometimes didn't pay much attention, so sometimes they were scared because the fetch was going in front of them, but they didn't know that the robot has collision avoidance and user avoidance. So yeah, that was interesting because we know that the fetch was programmed to do that, but no, all the people know that, and it's really hard for a robot to tell to people what's happening next.
Wonderful, thank you. Well, you guys did a great job. The video made it look like it was easy. And Jenna says, thank you.